We're actually generous enough to have Santiago Alvarez from Cisco come in to be able to give us a little bit of overview on OpenConfig to do a little tutorial as well as show some coding on how to get things done. We also have in the audience Anish Rick from Google, who is one of the main people involved in OpenConfig consortium. So he'll track what Santiago is saying. Without further ado, thank you.
All right, guys. 2 years ago, the OpenConfig group started making public their data models. And with that, it started a process of trying to accelerate the transformation in how networks are traditionally managed. So an exercise that I wanted to do was, okay, it's been 2 years. What can it be done today with what has been accomplished so far? And actually, you will be hopefully pleasantly surprised with the amount of work you can do and the amount of progress that has been made, not only from the point of view specifying data models primarily, and also getting those data models implemented into products. So in this presentation, I'm gonna take a very pragmatic approach. I'm not gonna try to give you the holy grail on OpenConfig, all the technical details. I'm gonna do kind of a quick overview. We're gonna zoom in into a specific set of data models that, that I think probably are ready for, for experimentation and usage in your own networks. And we're gonna see a test bed, a particular workflow implemented with those models. And we're gonna implement the whole workflow using OpenConfig data models, and we're gonna see a deployment of a peering configuration doing the complete closed loop validation of that configuration. All right, so let's talk first about a quick introduction of OpenConfig. I'm assuming most of you have heard already what OpenConfig is trying to achieve. It's basically a group of operators that get together to come up with specifications that will transform network manageability. And they wanted to have a very user-centric view. It's a working group, as they define it, by operators for operators. Okay? They wanted to be, if you want, their own architects or architects of their own interfaces to network manageability. The initial specifications for data models started to come out 2 years ago. I think the work probably started like 3 years ago. And in the last 2 years, there's been a growing number of implementations already available. And you get here a quick enumeration of the operators that are members of the organization. I said that OpenConfig started to deploy or to specify data models in the last 2 years, right? And for most people, kind of so far, when they think OpenConfig, they think about data models. When you really zoom in, you realize that they're trying to tackle not just the data model piece. The data model piece was the one that was addressed initially. That defines data models both for configuration and operation, using Yang as the modeling language, as probably most of you know. It's kind of it's not only a standard track modeling language in the IETF, but it also has become, I think it's gained enough traction in the industry to kind of become also the de facto standard for defining data models for networking. However, the OpenConfig group also is trying to define their own management interface, their own management protocol. GNMI or gRPC network management interface is the set of specifications that they released. I think that happened, if I remember correctly, earlier this year, maybe late last year, I don't remember that exactly. And more recently, they also produced a set of operational RPCs. These operational RPCs would allow you to run remotely commands on the device. Examples of that, for instance, would be clearing statistics encounters on the device or initiating a ping from a device. Okay, so they're really, at least so far, there are three main tracks that they are working on. One of them is the data models. The other one, as I said, is the main management interface, how to do configuration management with a set of RPCs that they define and that uses gRPC, and also the operational RPCs. In addition to this, I would say probably there's seems also a fourth track of tools. So they've also invested to some extent in providing tools. For the rest of this presentation, I'm going to focus specifically on the data model piece. Okay, so we're not going to talk about GNMI. We're not going to talk about GNOI. We're going to focus on the data models, see what data models are available, what structure they have, kind of understand those models at a high level, and see how those models can be used to implement a specific workflow. Before we review the structure of some key models, let's understand at a very high level kind of some of the model principles that this group applies. The first thing to notice is that they use a modular approach to module definition. So there's not a single Yang model for configuration or a single model for operational state. They have components or functions. Each of them have their own dedicated model. So a simple example, for instance, BGP will have its own dedicated module. You will not have a single monolithic model for all OpenConfig. One of the design principles that they have applied is consistency. And consistency, I guess I don't need to sell anybody on the value of consistency. Consistency automatically leads to ease of use, right, to usability. It makes it easy. You find common patterns that repeat often throughout models and makes it much simpler to use the models. They combine configuration and operational data in the same data models. In Yang, you have the option of creating data models that specify only configuration or specify configuration and operational data, or you can combine, the language allows you to combine both. In the case of OpenConfig, they actually combine. So if we look at the BGP data model, the BGP data model combines both the configuration and the operational data for BGP. They go one step further in differentiating the operational data. In Yang, either a piece of, or a node or a piece of data is either config or operational. In the case of OpenConfig, they try to differentiate between applied config and derived state. So you have the config, what is traditionally the configuration is the intended configuration on the device. In addition to that, the operational state captures both what was actually applied as configuration and the derived state. Derived state is, for instance, counters and metrics that are the result of the normal operation of the device, right? The interface counters or the change in the BGP state of a session, for instance. If you see here on the right-hand side, very quickly, we see for a particular piece in the BGP model, we see some of the attributes that they have for BGP neighbor transport, and we see a bunch of configuration data, TCP, MSS, MTU discovery, etc. And we see the state portion of the model for that particular piece in the model. And you realize that they clearly separate config from state. And we see the pattern that the configuration data is repeated under the state. The portion that appears under the state is actually the applied or what is considered to be the effective configuration running on the device. And we see here 3 more leaves underneath that basically would constitute derived state for BGP neighbor transport. Another interesting principle that they have applied on how they define their models is that they choose to use semantic versioning, which actually I think is a nice characteristic. Because these models in real life, the ultimate goal for these models is to accelerate automation, right, and software automation. And semantic versioning is a very natural concept for software development. So Yang typically uses the concept of a revision that is more of a timestamp. And in Yang, at least the IETF recommendation is to make data models always backward compatible. And that always comes at a big expense. If you really want to, it is okay when you start from a brand new model, but if you fast forward as models evolve throughout the years, they can accumulate a lot of changes. So I think the semantic versioning actually opens the door for a very pragmatic approach on data models in which you sustain backward compatibility to some extent, and you have some very well-defined points where you actually break backward compatibility. So let's look a little bit more in detail how the models are designed. So I mentioned models have both configuration and state in the same model, and a pattern that they use, a design pattern that they use, is to declare all the configuration under a config container and define all the state under the state container. So at pretty much any point in the model, you can look for two main containers, two main sections, one that defines the config, another one that defines the state. And you're always going to see the pattern that the information that is in under config, or the leaves that are under config, they also going to show under the state, because remember the concept of the intended versus the applied configuration. Okay. Another pattern that they use, design pattern they use for the model, that this I would say is very common for Yang models in general, is that they use the concept of a container to enclose all the elements of a list. So if we see here on the right-hand side, I captured here a piece of the BGP model that defines neighbors. Okay, we see that there's under BGP, which is the root of this model, there's a container called neighbors that groups all the neighbors configured, or the neighbors that are known to the device. And under the neighbor, that neighbor has a list represented here by this asterisk, and there's a key that identifies each of the entries in that list, which would be the neighbor address. So this leads to another pattern that when you're new to OpenConfig, it may become, sometimes you're gonna see it through the examples that I'm gonna show later in the presentation. And is that if a list in Yang, which a list is more like a hash or a dictionary, if a list has a key, that key has to be a leaf under the list. So we see here neighbors, for instance, each neighbor is identified by a neighbor address, and we have here the field where the neighbor address is specified. But the neighbor address is actually a piece of configuration. And in the notion of, or in the design approach taken by OpenConfig, the neighbor address is piece of the configuration. So you're gonna see that actually the neighbor address happens under the config container, okay? So what the OpenConfig models do is that actually the key is gonna be defined under the config container, and the neighbor address that acts as a key is a reference to that data that is inside the container, okay? And if you find this a little bit confusing, this slide, you really have to, I guess, understand a little bit of the basics of Yang and the basics of how things are encoded. But the good news is that the rest of this presentation, I really made a big effort, so you don't need to have any preliminary or have to deep knowledge on Yang, okay? But if you ever wonder why some fields tend to show duplicated, your data seems to be duplicated, this is the root reason for that. Another area or design approach that they took and it's been a little bit controversial was that the Yang language, in the Yang language, you can define patterns for strings. Okay, for instance, interfaces. Interfaces are a very well-defined pattern, right? The name of an interface. And the specifications of Yang, those patterns are defined with regular expressions that they follow the W3C model. In the case of OpenConfig, they chose to use the POSIX models, the POSIX flavor of regular expressions, because of the additional support for POSIX regular expressions instead of the W3C. I would probably say that most tools today probably compensate for this difference, and there's been a lot of dialogue going back and forth. And I think last time I checked, there's a kind of a trajectory of how to reconcile the use of regular expressions going forward in OpenConfig to make sure that it sticks to the Yang specifications and doesn't create any issues for any existing tools out there. So before I move forward, let me just summarize really quick things that you need to remember. You have a model for different components. So for instance, for each protocol will have its own data model. The data model is going to include both configuration and operational data. Okay. we saw that the config typically resides under a config container, right? The state resides under a state container, and the state is going to have the applied configuration plus derived state. Okay, so those are kind of at a very high level, so key concepts that you want to remember. Also, if you have to deal with the files, with the YAM files, because you're using your own tool chains or your own YAM tools, and you want to play around with the models, these are some naming conventions that you may find useful to understand. The first one is how they name their modules, and it's basically they use the notation OpenConfig dash in the function. So I show on the right-hand side the example. For instance, the model for BGP would be OpenConfig dash BGP. The file name, of course, the file is going to end with extension yang. Within a particular function, you have additional models or modules or submodules that are used to define the entire function. So for instance, in BGP, you're going to see that you don't have a single OpenConfig BGP yang file. You have additional models that in aggregate define all the BGP functionality. So an example of that would be OpenConfig BGP policy, okay? And I'm showing here just one example, but if you look at BGP, I think BGP now has probably like 7 or 8 files at least that are used to define BGP functionality as an aggregate in OpenConfig. Okay. The prefix notation, this is a little bit of Yang terminology. Starts with OC for OpenConfig dash in the name of the function that quite often is abbreviated. If it is a subfunction, you see the same pattern. So OC BGP and OC BGP poll are examples of that. Again, if you're not manipulating YAM files directly or using YAM tools, a set of YAM tools, maybe these are details that you don't need to worry about it. But sometimes, if you ever wonder, when maybe you're examining some of your encoded data and you're trying to understand where does this name come from, this hopefully will give you an idea of the logic behind it. Another naming convention that they use is for the namespace. In particular for the case of XML, you have a namespace for your data, and they follow the notation of openconfig.net.yang, /yang/function subfunction. So I show the examples of the namespaces that you may see for BGP or for one of the subfunctions of BGP. In terms of identifiers, and this is important because this is going to be reflected even if you don't manipulate the files, the YAM files, and you don't use your own YAM tools directly. Some of these details are going to be visual to you. Is the identifiers, the individual nodes in that tree that we saw. They are lowercase with dashes for regular nodes. Only for enums, for enumerations or identities, the notation is different. It uses uppercase with underscores. Okay, so that's a little bit in terms of style what you're going to find throughout the models. I mentioned before that they favor or they make use of semantic versioning for their models. Their model still has a revision because that's the mechanism that Yang defines. But in addition, they specify a semantic version for the model. Okay. They follow the typical or I would say the industry consensus for semantic versioning of 100 being the major, first of all, having 3 digits, right? You have a major release, a minor release, and a patch. And 100 is kind of supposed to mark the initial version of the model for which there are enough implementation progress in the industry. And it's kind of, it's possible to start implementing them or experimenting with them. So I kind of marked that just to give you an idea. I put a list of all the models that they have defined so far. I think I only missing here the Wi-Fi models that I think got pushed last week. But other than that, it should be an entire list of the models. The models that you see on the left-hand side are models that already have made it past that initial milestone of version 100. Many of them are actually past version 1.0.0. I think in BGP in particular, it's probably like 3.0 or 1.0 or something like that. So I just made a very clear demarcation of models that have crossed 1.0.0 and the ones that have not. Okay. And for this presentation, the models that I'm gonna zoom in and give you examples, and we're gonna build this test bed, this little demo. Most of the models are actually gonna be on the left-hand side, the models that have already made 1.0.0, with maybe an exception of a couple of models. If there are any questions, by the way, I welcome questions at any point. All right. All right, so let's start zooming in. Models are obviously can be rather big, and there's a lot of detail in them. But I just want to kind of give you at a very high level a flavor of what kind of structure they have. So I'm going to go through a subset of the model. I think I'm going to review a total of 4 or 5 models because those are the ones that we're going to be using later in the example. Okay. So let's take a look first at BGP. This is the, if I remember correctly, the first model that was published by the OpenConfig group. And you're gonna see very quickly that there are 3 top containers. The root of the model is BGP, no surprise. And there's 3 main containers that are defined. Global for the global BGP configuration of the device. Neighbors that contains all the neighbors known to BGP, and peer groups. Okay, this model obviously has support for multi-protocol operation, and as I indicated before, it follows the notation of having both config and operational data embedded. Before I actually go much further, let me make a note, because some of you, maybe the people that have been following the OpenConfig work more closely, know about the network instance model. So the network instance is a model that I'm not going to describe here, because again, my focus was on what can be done today with the implementations that are available. So the network instance basically defines virtualization and virtualization services or multi-tenancy for routing, and is going to affect the structure of different data models, in particular BGP. So the flavor that I'm showing here of the BGP data model is the BGP data model before the network instances. Okay. So as I mentioned, 3 main components: global, neighbors, and peer groups. If we zoom in a little bit into the neighbors, we see that on the neighbors, again, you see a list of, unfortunately, I don't have a laser pointer, but you see neighbor star basically indicates that you have a list of neighbors, okay? That the key is gonna be the neighbor address that's in the square brackets. And we see at a very high level that there's config, state, timers, transport, error handling, and login options. I think there's actually a few more pieces of data under each neighbor, but I couldn't fit it on the screen. But that's basically at a very high level. Okay, so all the config container will have configuration that is specific to that particular instance of a neighbor. The state will have the state to that particular entry of the list. Timers, transports, error handling containers, they will have their own config and state container inside them. Okay, so again, that pattern of seeing config and state containers, you're going to see that pattern be repeated throughout the model. Okay. On the right-hand side, we see the configuration, or not the configuration, the data model for peer groups. So very similar pattern. There's a top under BGP. There's a top container peer groups that has a list of peer groups. You see peer group star indicates that it's a list, that you have multiple of those. And the key is the peer group name. And we see the 1, 2, 3, 4, 5, 6 different containers. And again, I think I had to crop the output. So there's at least 6 containers that reside under each peer group. We find the common pattern of a config and state container. Okay, and as I mentioned before, timers, transport, error handling, login options, they will have their own config and state containers inside them. Okay. I'm showing here, depending on because I had to fit the app. First of all, I wanted to avoid unnecessary detail, and also I had to fit it on the slide. I think in some cases I use 2 to 3 levels of depth in the model. Sometimes I go to 4 levels, and quite often I'm just traversing a specific path through the model, right? Remember, the model is a tree, so I'm kind of, if you have to think about it, I'm kind of moving a sliding window and try to zoom in through small pieces of the model to kind of give you a very high level view of how the model is defined. So that's for BGP. So for BGP, again, 3 main components: global, peer groups, and neighbors. Okay, and each of them has a list, with the exception of global. Global is just the global configuration of BGP configuration and state, I should say. All right, so let's take a look at the routing policy. So routing policy is defined in a different model called OpenConfig routing policy. The root is routing policy and has 2 main containers. One of them defines sets, and the second one is policy definition. The policy definition is actually the definition of the policy. The defined sets are going to be the sets that are basically going to use to match conditions in your policies. Okay, it can be a prefix set, it can be community sets, it can be ASPAT sets, it can be many different things. Okay, the routing policy model doesn't define the defined sets and doesn't define all the attributes for policy definitions for BGP directly. That actually is defined in an augmentation. So if you look at just the OpenConfig routing policy, it's going to have a lot of constructs for routing policies, but you're not going to see BGP data there. There's actually a BGP policy augmentation. So there's a separate Yang definition that augments routing policies to make them BGP capable. And I think I have one slide to describe this. Okay. I put this slide, excuse me, more as a reference. You can review it later, but it basically has the evaluation rules that are followed for the routing policy. So I would say this should be pretty common behavior that you find in routing policies. But actually, I appreciated the defined description of what the logic is supposed to be. This actually, the description is embedded in the data model itself. Remember, the Yang models are self-documented, so the documentation strengths of the model actually gives you a good idea of how the routing policies are meant to be evaluated. Okay. Let's take a look at defined sets. I said there are 2 main components of a routing policy: defined sets, that are sets you're going to match against, and the other one is policy definitions. So I'm going to describe them really quick without the BGP augmentations. Remember that the BGP options are brought into the model with augmentations. I'm going to talk about the augmentations in a later slide. So the basic routing policy model defines prefix sets, defines neighbor sets, and tag sets. Okay. Those are different sets that you can use for conditions to match on your actual policies. And if we see on the right-hand side, the policy definition, we see that you have a list of policy definitions. You see probably in the 5th line, maybe, there's policy dash definition star, right? So it tells you that you can have multiple policies, that the key is the name of the policy. Okay, and you see that there's statements container further down, and then you see a list of containers. You see statement star, again, the star tells you it's a list. Each statement has a name that acts as the key. And so each policy, you have a list of policy, and within each policy, you can have one or many statements, and each statement has conditions and the actions that are going to be executed in the policy. Okay, they should be very forward behavior. I think it's a very straightforward pattern to understand if you're familiar with routing policies. So let's take a quick look at the augmentations, the BGP augmentations. Okay, those, if I remember correctly, are defined in the OpenConfig dash BGP dash policy. Okay, and you see that these augmentations define, as you would expect, community sets. any decent BGP policy, you need to match against communities. Extended communities and AS paths. So these are extensions brought into the routing policy model by these augmentations. And these are the augmentations to the policy definition, and in particular to the conditions and the actions. Remember, under each statement, you have conditions and actions. So as you would expect, these augmentations allow you extend conditions so you can match on community sets, match on extended community, AS path, blah, blah, blah. On the right-hand side, you see the enhanced or the augmented actions, setting AS path prepend, setting a community and extended community, etc. Okay, so pretty straightforward. Again, if you're familiar with BGP and routing policy configuration, this should be something that you can easily relate to. Any questions on the BGP or routing policy so far? All right. So let's look now at interfaces. So interfaces, the interfaces model allows you, as the name suggests, is the model that has all the config and operational data for interfaces on the device. It has 4 main containers under, well, first of all, it has a top container that is interface. You have a list of interfaces, right, indicated by the interface star. Interfaces are identified by a name. And each individual interface is going to have a config block, it's going to have a state block, it's going to have a hold time, and it's going to have sub-interfaces. In this model, actually, each interface or interfaces have sub-interfaces in them. And if you want to, for instance, configure the IP attributes for an interface, all that IP configuration actually happens on the sub-interface. There's a series of augmentations. So if you look at the base OpenConfig interfaces model, you're going to see the structure that I described here. But then you'll see that in the same way that BGP has a collection of additional files that either augment or complement the definition of BGP. In the case of interfaces, you're going to see the same models or the same approach. You're going to see that there are augmentations for bundles, for Ethernet attributes, for IP, and also for VLANs. And I'm going to touch on some of them. So the bundle and the Ethernet augmentations, we're going to take here a quick look. So you see on the left-hand side, the augmentations for aggregation, basically for bundles, okay? So you see that there's an aggregation top container. Again, you see the same pattern of having a config block and the state, and having an LACP block under that has config and state and members, okay? So these are augmentations that enable bundles based on the characteristics defined by the base OpenConfig interfaces model. Okay. On the right-hand side, we see the augmentation for Ethernet. Whoops. We have the augmentations for Ethernet attributes. So we see under an interface for Ethernet interfaces, again, we have a config and state block. Under config, we have MAC address, auto negotiate, duplex, port speed, enable flow, etc. And again, you see the same pattern. Remember the same pattern that I described before? You see the config block, which is the intended config, and you see all those leaves repeated in the bottom part under state that's supposed to represent the applied configuration. And we see some incremental, in this case, some derived state leaves, the hardware MAC address counters, and I think I have to crop the output. So I think there's some additional state information that you can gather or you can manipulate for Ethernet interfaces. All right, let's take a look at IP. IP interfaces are also an augmentation of the base interfaces model. So the name of the module is OpenConfig IF IP. And you have augmentations for IPv4 and IPv6. IPv4 we got on the left, IPv6 on the right. And under IPv4 and IPv6, actually, I think the first 4 components under that container are the same. You got your address, you can do neighbor configuration, and you have other config and state that resides at that level of the model. And last, on interfaces, we have the VLAN, the augmentations for VLAN, to have VLAN support on interfaces. Again, on the left-hand side, on the right-hand side, I think left-hand side, right-hand side is with augmentation, with bundles, sorry. VLAN with bundles, and the left-hand side is port. But it's basically the same data that is augmented, whether the interface is a bundle or is not a bundle. And you'll see the common pattern of a config block and a state block. Right. So that's it on interfaces. Any questions on that? Okay, so let me just summarize on the interfaces very quick. You have a base interfaces model. You have augmentations for bundles, for VLANs, for IPv4, IPv6, well, actually for IP. Defines both IPv4 and IPv6 and Ethernet. I think that hopefully I covered all the augmentations. And one key concept to remember is that IP attributes are always defined under a subinterface. Yes.
Philip Matthews. Can you hear me?
Yes.
What's the state of OpenConfig? You know, obviously they sort of have one view of things, but not all vendors implement exactly, you know, the same view. How does OpenConfig give any comments about how you map what their view of the world is to what other people's view of the world is?
So they're basically defining an abstraction on top of, you know, different vendor implementations, and I think their goal is to remain on that abstraction layer. So it's really up to the vendor to find the correct mapping between that abstraction provided by OpenConfig and their own implementation. If the mechanism that Yang provides is, if for whatever reason, it's not an ideal, but at least it's a suitable solution, is if for whatever reason the device is not capable of supporting the data or the capability, it can deviate. So via Yang, the device can declare in Yang itself that out of this model, there's these corner cases, these leaves, these containers that I'm not able to support. And even though that's not, there's always a limitation, but at least programmatically, you can detect those situations and you can plan for them and you can handle them programmatically. Yes. All right, so let's take a look at next at OpenConfig telemetry model. So I'm assuming hopefully all of you guys have heard about streaming telemetry that basically provides a mechanism to kind of revert the old style polling of polling the device to be able to manage the network, to kind of reverse the flow and instead doing the streaming in most cases directly from the device. So there are three main abstractions that are defined in this model. You got sensor groups, you got destination groups, and you got subscription. Actually, let me talk a little bit more about them. I thought I had more detail. So sensor is basically defines what is the data that you're interested in that it should be streamed. And we're gonna see later in the use case, in the demo that I put together, that we're gonna define two sensors, one of them being interface and the other one being BGP, because we're interested on the device reporting constantly what's the state of BGP and what's the state of the interfaces. The second main abstraction in the model, which is the destination groups, is basically the definition of definition of the destination that is going to collect that data that is being streamed by the device. Okay? And the subscription is the combination of a sensor group and a destination. I'm kind of oversimplifying, but at a very high level is that, right? So the sensor group is what you want the device to stream. The destination is what you want the device to stream it to whom. And the last one is that subscription, which is the combination of, I want to stream this to this destination, okay? that's at a very high level. Any questions on that? Okay, so we basically reviewed, I think, a total of 4 models with their augmentations. We started with the BGP. We talked about the global neighbors and peer groups. Then we talk about routing policies, right? That we said it has defined sets and policy definitions. Then we talk about interfaces with all its augmentations. Then we talk about telemetry with the 3 main components: sensor groups, subscriptions, and destination groups. So what I wanted to do next was to kind of combine those 4 models and try to see if I can implement a workflow. And the workflow that I chose was to configure and validate peers. So I created a set of scripts that are going to use OpenConfig to automate this workflow, to programmatically configure the peering relationship between ASBR1 and ASBR2, and do that at the same time that the configuration, the operation is validated. Okay, so the entire flow would be first. The 2 initial steps is kind of day 0 configuration. It's just enabling ASBR1 for a particular routing policy that is going to be used for peering. So it's something, you typically, if you're going to push some peering configurations, the device may already have some routing policies that have been pre-configured, because these routing policies are typically reused across many peers, right? So I'm going to show an initial step of configuring a routing policy on that device. Then a day 0 configuration of enabling telemetry on that ASBR1, so that ASBR1 starts streaming to me all this OpenConfig state for interfaces and for BGP. And the third step on this workflow will be for a script on this node to read a peer configuration of the peering that we want to do between ASBR1 and ASBR2. And based on that local configuration that is read from a local repository, all this is actually sitting in a virtual machine, a single device. So I read that local configuration, and I'm going to configure the interface, wait for the interface state to be pushed back to me, and only when I'm able to get the stream data coming back from the router that the interface is up, the script will continue execution, and then it will configure BGP, and it will start monitoring the BGP data that is being streamed back to the router. Okay. So if all goes according to plan, this is going to work in front of your eyes. So cross your fingers. All right. So before I show the details of the configuration and we execute the scripts, let me talk a little bit about the open source tool chain that I'm using in this testbed. So the first thing that I'm using the YDK, or the YAN Development Kit. That is basically an SDK that gives me Python and C++ bindings for the data model. So this allows me in a very simple way to write Python code against an OpenConfig data model. And it takes care of not only giving me those classes and allowing me to create those objects, but also doing the data validation. So my script, before it sends any configuration to the router, the data will be validated. And the SDK also provides the abstraction of the communication to the router. In this testbed, we're going to be using netconf, and all those details are completely abstracted. Yes?
My name is Rami Hashish from Noor Data Networks. Can we go back to the...
Sure.
Okay. Here, in step 3, you loaded the peer configuration, and then you configured the new configuration. So, assuming it's not a green field, okay? We're configuring a brown field. How can we verify? I mean, if the loaded configuration made me change my mind in what I need to configure, or made me discover that something needs to be amended before applying my configuration, how can this sanity check be done?
I didn't quite get the question. You're saying if you have a brownfield configuration and you have configuration already on the router, how can you verify whether the configuration is present on the device? Some configuration is already present or not?
I just want to make sure that my configuration won't conflict with any of the existing configuration.
Oh, how can you verify that? Okay, it's a long, it can be a long conversation. To give you maybe a very quick answer, there are different ways in which you could do that. If you're from a theoretical point of view, you can retrieve your configuration. If your configuration is compliant to a model, actually there's a lot of validation that you can do off box, just leveraging the power of Yang and the power of the data models, okay? If that's not because of the capability of the devices or because of the characteristics of the configuration that you have, that's not realistic. Ultimately, you have to kind of rely on the configuration manager on the router to arbitrate those things. So if you're trying to push a configuration that is incompatible with configuration that is in the device, for instance, if you were to use netconf, but if you were to use RESTconf and any other protocol or mechanism, gRPC, to try to configure, the configuration manager on the device will tell you that the configuration you're trying to push is incompatible.
Okay. I was asking about if it's not about compatibility with the device. It might be I need to keep for example, the MTU on on a certain interface as is. So these types of sanity checks, I need to keep the value of some certain specific parameter.
Yeah. So again, I think there are different approaches to do it. I mean, you can off box. You probably want to do all that validation. You can retrieve your configuration and do that validation offline. We can maybe, if you want, maybe we can have the conversation at the end, because the intent of this demo, by the way, you're not in. The assumption is not you're going to run with this and you're going to try to do it in your network. I just tried to build a quick, simple setup to kind of show what is possible with OpenConfig model. So the focus, I want to make sure that it's more on the data models and what can be done with the models, not so much on whether this is an appropriate workflow to deploy a peering configuration or not. Okay? But I will happily discuss at the end.
Sure. Thank you.
Okay. All right, so let me keep going through the tool chain. On the collection side, remember that I said we're going to be verifying when we configure the interface and we configure the BGP, we expect data to be streamed back. So we need to have some kind of collector, and we're going to use an open source project called Pipeline that is going to collect that data. The data is going to come to that collector in protocol buffer encoding, and it's actually going to be transforming it to JSON. And this collector can act as a producer into other platforms. So in particular, in this test bed, we're going to use in Kafka, which is also another open source project, as a message bus. So Pipeline is going to be receiving the data from the device in protobuf. Is going to transcode it to JSON, and it's going to dump it on a message bus. And my scripts that are doing the deployment of the peer are actually checking the state of BGP and the state of the interface reading from that message bus. Okay, so let's start looking at the details of the configuration. What I'm showing here is actually kind of configuration examples or instantiations of particular data models. In this case, because of the tool chain that I'm using, and also because it's more compact to show it on the screen, I'm actually not showing the configuration encoded in XML or JSON, because actually it would be much longer, much more difficult to fit it here. So I'm actually showing the Python objects that YDK allows me to configure, okay? And you should recognize, if you remember from the quick overview that we did on routing policies, some of the abstractions that I mentioned there you're gonna recognize here. One of them, for instance, a prefix set. So we see here in the very first line that we're defining or creating a new prefix set that is actually adding two prefixes. It's adding 10/8 with different mask ranges, and 172.16/12 with different mask length ranges, okay? So basically we're defining the configuration of a prefix set. We're gonna try to match these two prefixes because we're gonna drop prefixes that match these two sets, okay? So this corresponds to the initial part of my routing policy configuration. If you look at the very last line, you're gonna see the path. You should be able to recognize the path that we talked in the routing policy model. The root is routing policy, and on the routing policy, you have defined sets. One of the defined sets that you can define is the prefix set. And in this case, I'm appending the prefix that I just configured here in this top part, okay? So again, the path of my objects completely mirrors the structure of the model. So this is my actual policy definition, okay? And this may be, I recognize, maybe too much Python and too much OpenConfig for some of you, but maybe two key blocks that you want to understand. We see here the definition of the first statement. This policy is going to have two statements, one of them called drop prefixes that references that prefix set that we defined in the previous slide. And it has a second statement that basically is a default reject route statement, okay? I'm sorry, the reject is the action for these drop prefixes. The second statement is the bottom part. The second statement is an accept route. So basically this is a policy with two statements. One of them it drops prefixes if they match that prefix set, and the second one just accepts anything else. And again, we see here the path, routing policy, policy definitions, policy definition, and we're appending the policy that we just defined in this top part. Okay. Any questions on that? All right. The order. The order, yeah, that's a good question. What about the order? In general, in Yang, I don't know how many people are familiar with all the details. In Yang, containers, which is a single mechanism for grouping data, does not have ordering. So at a certain level, there's no ordering between containers. And another abstraction in Yang is the concept of a list, right? That has kind of multiple records. In this case, you have a list of statements. You can have a list in which the order is significant, a list in which is not significant. This is an example of, obviously, of a list where the order is significant, and in the model is 99.99999% that is defined as a list that is ordered by user. So basically, the order that the user defines for the statement is the order that the device has to implement. For many other lists, the order is not significant. For instance, for your neighbors, for your BGP neighbors, whether one BGP neighbor happens before or later in the configuration is not necessarily relevant. And Yang as a language allows you to do that. Let's take a look now at the telemetry configuration. Remember, in telemetry, we said the three things that you need to in any telemetry configuration. First of all, what is it that is going to be streamed? What's the data I care, right? What's the data that I want the device to send to the collector? Okay, that's one thing. The second thing is the destination, right? Defining who's going to be receiving that data. And the last one is the subscription, that basically is the definition of in simple terms, the combination of the sensors and the destination. So in this case, we create a sensor group with two sensors. We're telling the router that we're interested in the OpenConfig interface. So basically, I want to get all the state of the interfaces. Okay, I create one sensor path that I reference here. And here's the definition of the other sensor path. And I'm saying I want all the data for OpenConfig BGP neighbors. Look that I'm asking for very specific data. I'm not interested, for instance, in peer groups in this case. I chose to do it that way. I could ask for stream to me all the BGP data, but in this case, I'm saying stream to me BGP neighbor data. I don't care about the global. I don't care about peer groups, which is the other two main branches of the BGP model. Again, if you follow the path of the objects, you realize that it's the same path that we were talking before. The root of the telemetry model is telemetry system. After that, you have sensor groups which is a container of all the list members, and we have one sensor group that we're appending to that list. All right, the second main component, the destination. So in this case, I call a destination that is pipeline. Remember, pipeline is going to be the collector that is going to receive the stream data, convert it to JSON, and put it on the Kafka bus. So the destination is called pipeline, and this is the IP address and the port that is going to be used. In this case, the box is streaming the data in protocol buffer encoding, and it's using TCP transport in this case, in case you care about the details. And the last piece of the configuration for the telemetry is the subscription, where we combine the sensors that I define and the destination, and I specify with what frequency I want the information. So we are creating one destination that references the sensors that we defined previously. It references the collector, the destination that is called pipeline, and we're specifying that we want the data every 10 seconds. Okay? So I want counters for interfaces and for BGP neighbors to be streamed to that destination in protobuf encoding every 10 seconds. Yes. If the frequency can be modified, lower, you mean? Initiated. Oh, it can be negotiated. You can, I don't think it can be negotiated per se. I think when you do dial-in, there's two models of telemetry. This is the dial-out model. You have dial-in. I think the dial-in, the device could reject your configuration if you're trying to set a frequency or an interval that is not supported by the device. All right. Any questions on that?
My name is Talak from eBay. So if you go back one slide back.
One slide back.
Subscription
Yes.
endpoint. One more slide back.
One more.
So can we do the subscription outside of the box, right? You subscribe to the specific path instead of configuring the destination on the box itself, meaning initiate the subscription.
If you can define the subscription of box and just tell the box you
subscribe to the specific path you want the data back. So right here, we're specifying what is the destination and port.
yes.
But can we do that outside of the box? So, you have a set of collectors sitting there that subscribe to a path that you're interested in. So
Off box you can define where you want the data to be sent to. That's what we're going to do here. This configuration actually is going to be pushed into the box, right? Or you can have a dial-in model. I don't know.
yeah, so I'm talking about the dial-in model where you might have like a group of collectors sitting across the network. You can subscribe to a path instead of telling box to send send to a specific destination.
Yeah, you could do it. I think the model that the OpenConfig is pursuing for that is to use actually there's an RPC in the GNMI specification that I think is supposed to tackle. You get the expert on the left-hand side. We can maybe have the conversation afterwards on that. But I think that's the approach that will be followed in that case.
Thank you.
Yeah. Any other question? Okay, so I went very quickly to two pieces of configuration that is kind of day zero configuration that is going to be on the router before actually configuring the peer, right? The idea that we want to pre-configure the policy and we want to pre-configure telemetry, okay? So this is the beginning of the workflow where we're going to configure very specifically a given peer. And what I do is what I'm doing here is I created a local definition of what a peer of the peer I want to set up. And this is my own JSON file that I created, right? It's on a local format that I created, right? That specifies on ASBR1, my autonomous system is 65001. On this particular interface that I define here with those attributes, I want to configure a neighbor to that destination, and my peering address with that neighbor is that, okay? So what I'm going to be showing in the last part is actually the automation of reading this data, using that data as input for configuration scripts that configure the interface and also going to configure BGP. But also my script is constantly monitoring the Kafka bus. When it pushes the interface configuration, in this case, the configuration on gigabit Ethernet 0000, it's going to start watching in the Kafka bus, see if that interface came up or not. So it's not going to be polling the device. Okay, that's the key difference that you need to notice here. So my script is going to wait for messages coming from the Kafka bus to see if that interface came up. When the interface comes up, it's going to move to the next stage, which is pushing the configuration using OpenConfig, pushing the BGP configuration for this particular peer, and again, listen on the Kafka bus for that BGP session to become established. Okay? Yes?
I just have a quick question. Could you please go to the last slide? So how do you this model fit into a device can be virtualized? So I can run a VRF or run a virtual instance. How can this model can fit in kind of operational requirements?
Yeah, right now, and I think I mentioned that earlier in the presentation. In the future, you will have to use additional models to be able to do that. In particular, you will need to have a device that supports the network instance model, because that's the model that gives you virtualization or multi-tenancy on devices. With the models that I have here, that is not possible. Okay, but I think the implementations of the network instance, either you may have some ready out there, or if not, they should come out pretty soon. So let's take a look at the IP interface configuration. Remember, my script has to read this basic interface configuration and needs to send that to the router using OpenConfig, sorry. So this is the configuration in my snippet of configuration, also in Python. So this is my gigabit Ethernet 0 interface. I put the description of the interface. And remember, all the IP configuration happens under a sub interface. So here I'm creating a sub interface under that interface, putting the attributes of the IP address that I want and the mask that I want, okay? And that's the two basic pieces of configuration. Creating the interface, put the basically the description on the interface, defining a sub interface, an IP sub interface for that interface, and put the basic address on the interface. I said we're going to validate. We need to validate the state, because I don't want to, in principle, I don't want to configure my BGP if my interface didn't come up, okay? So the device is going to be streaming data back to me about all my interfaces. So the path that I'm going to use, I'm using a very simple validation for my demo here. So the path that is going to be used to monitor the interface is the operational status under the sub interface. So I'm going to look for the operational status on gigabit 0000 on the IPv4 sub interface, and I'm going to look for that operational status to show up. Okay, these are all the possible states that you can have associated with operational status. Okay.
Just out of curiosity, how are you streaming the data? Are you just syslogging, or are you using some other mechanism
No,
to?
we're using the beauty of telemetry, what I was describing before. So we're telling the router to stream that data. It's actually model data. So it's the same operational data defined in the model. It's actually the data is encoded, in this case, in protocol buffers, and it's a stream on a TCP connection back to the pipeline collector. So it's very sent way more structure than syslog, and it's being sent way more compact than text-based. Yeah. So if you're not familiar with telemetry, I will highly recommend you take a look at it. It's a much better way of doing monitoring your network device in real time. So let's look at the last piece of the configuration for my peer. If my interface came up, the last thing is actually configure the peer. And here I'm mixing maybe more, but I wanted to show a more complete BGP configuration. Remember, BGP has 3 key pieces, global configuration, peer groups, and neighbors. I could have done just neighbors. I tried to get fancy, and I put 1 peer group configuration too. So here's in the top part, my global configuration in which I'm defining my autonomous system, and I'm enabling IPv4. I beg for mercy. I didn't do an IPv6 example. I promise next time it's going to be IPv6 only. But it's almost the same, right? You just do search for a 4, replace for 6, and the configuration will work. Well, I need to change the IP address too. I take that back. So this is the global, where we activate the IPv4 address. Then I'm defining a peer group that I'm calling EBGP. So we see here, EBGP is the name that I'm going to use. Under that EBGP peer group, I'm also enabling IPv4 unicast. I'm enabling that all these paths, again, are paths that come from the structure of the data model, the OpenConfig data model. Okay, they just happen to be Python objects, but they follow exactly the same naming convention, the same hierarchy. Okay, we see that we're applying the policy, okay, that we defined before on that peer group. Okay, and the next slide, we actually have the definition of the neighbor that uses that peer group that we defined in the previous slide. So this is the address that we read from that JSON file that is telling me the peer I want to connect to. This is the remote peer. Actually, I just realized I have a typo here, 65,002, by the way. And I'm referencing EBGP, the peer group that I defined before. After the BGP configuration is pushed, the last step is for my script to verify that the BGP session came up. And again, I don't want to be polling the router. I want to be listening to the Kafka bus for messages, telemetry messages that are being streamed from the router, and look whether my session came up or not. Okay? So I'm going to go under OpenConfig BGP, BGP neighbors, neighbor, state, session state. And I'm gonna look for that field being established. That will tell me that my session is, my BGP session to that neighbor has been established, and I'm passing, hopefully passing advertisements at that point. Okay. So we have 20 minutes, around 20 minutes to complete. So this is how the execution of the script looks, okay? We're gonna do it, and so basically what you're gonna see is the loading of the JSON file. The configuration will take place. The script hangs or stops at that point, waiting for Kafka message to verify that the interface came up. If the interface comes up, you get an OK, and it moves to the next step, which is completing the BGP configuration and waiting again for the state to transition, okay? So let's take a quick look. All right, so what I did, and this is, I'm gonna be pushing this to GitHub, so if you wanna try it later, I created a Vagrant environment that has all these scripts. It has the collector and Kafka, everything pre-configured, so you can. The only thing that you're not getting for free is the router, but the rest of the stuff that is open source, you have it. Okay. So let's take a look really quick. So we go under the demo directory. We have here the collection of different scripts. What I'm gonna do first is, remember, the router right now has not read the JSON file with the peering, doesn't have telemetry configured, or it does not have a routing policy configured yet. So I'm gonna show you really quick the script that configures the routing policy, okay? So this is basically the snippet that I showed you before in that slide, right? This is all my policy configuration. You recognize here the prefix, the definition of the prefix set. You recognize the definition of the policy, one statement, two statements, okay? So this Python script, basically, this is the step in the script where that object is created. And this is the step on the script when I'm telling the script, go ahead and create this configuration on the router. And what the script is going to do is going to validate that object that I created is valid with respect to the model. When it validates that, it's going to convert it to XML. It's going to generate the netconf RPCs. It's going to send it to the router. It's going to take care of doing the commit and all that stuff. So all that logic is completely abstracted away. I don't need to worry about doing any manipulation of XML, no manipulation of netconf. I don't need to worry about is my data correct or not. Hopefully, if the router of the script executes fine, it means that it was able to verify that my object is defined properly. Okay, so let's execute this first script. And the script takes one required argument and one optional. First of all, just for some sanity, let's make sure this guy is up. Yay. Okay. So let's do the configuration of the routing policy. Okay. Oh, it's hidden the CLI. Okay, no problem. We got you covered. I was counting on that trick, but that's fine. You guys want to see the... Okay, is that slightly better? Yes. Okay. So we're going to execute the script. The script has an optional flag that is -v to get the login. So we can see what the script is doing. Okay, so we see that the script actually converted that Python object to a netconf RPC. I see my routing policy object here. I recognize my prefix set on this first part. I recognize my policy definition, okay? So if the script converted this all to XML, it means that my configuration was valid from the perspective of the script. It sent it to the router, we got an okay from the router, it sent a commit, the router responded a commit. Okay, so we're doing kind of the day zero configuration of getting that policy before we actually start configuring any peers, okay? The second piece is gonna be enabling telemetry. Remember, we wanna get all the BGP neighbors and we wanna get the interface state. So what I'm gonna do here on the side, I have a very small script that is consume telemetry, okay? This is as simple as you can get in a Python. Basically, this script acts as a consumer of the Kafka bus. This script goes to Kafka and says, hey, any message, any telemetry message that you get from the router, give it to me. And this script is just gonna dump the JSON on the screen, okay? So this, by the way, is running on my laptop. So the router is somewhere in the cloud and it's gonna be sending messages to my laptop. And in my laptop, hopefully we'll get the JSON if everything goes according to plan. We should get the JSON messages on the screen, okay? So I just executed right now, since we don't have telemetry configured on the router, there's no messages coming at the time. So we're gonna leave that screen on the side, and that screen is gonna start getting populated once I configure telemetry. So let's take a look very quickly at the telemetry script. So again, here, if you review this, if you're interested and you review this later, these are basically the snippets that I put, right, for my configuration, where I define the 2 sensor paths. I'm gonna tell the router I'm interested in interface counters or interface state, and I'm interested in BGP neighbor state, okay? Here's where I defined the ports and the destination that I want, okay? Let me get my IP address. Okay. So we're gonna run this script. The script takes 2 arguments. First, the node that acts as a collector for the data, which is, again, it's gonna be my laptop, and the router we wanna send this to. Okay. And I'm gonna also enable the -v flag so we get the details of what's being sent to the router and what the router replies with, okay? So we see here that the script, all my configuration, my OpenConfig configuration got my OpenConfig telemetry configuration got encoded in XML. We see here from the namespace that is the OpenConfig. We see the destination group with one destination. We see the sensor groups with interface and neighbors. Okay, so that's the usual. Okay, here's where the emotion, the suspense comes. Is the router gonna respond? Oh, there you go. So we started getting the data back from the router. Okay, we subscribed for interface and BGP. And it seems that we're getting interface information, but if we scroll here, we only seem to see interfaces, okay? We don't seem to see any BGP. Any guesses of why the router is not streaming to me any BGP data? BGP hasn't been configured yet. All right, you get someone is paying attention. Awesome. All right. So right now we have kind of the base, the day zero configuration, which was getting the routing policy and get telemetry. At this point, we're ready to configure our peer, right? So I tried to make the demo kind of modular, and I created the validation step. Remember, when we provision the peer, we want to validate the interface and we want to validate the neighbor. So the validation, I made it as a separate script also. So I'm gonna show you what the script does. Actually, hang on, let me see. We're gonna try to validate at this point more. Hang on. We're gonna try to validate the interface. Is the interface up or not? Not validate. Yeah, interface. Okay, so we on ASBR1, we wanna validate whether that interface is up, and we're gonna use the Kafka message bus as 1992, right? And I'm gonna use -v just to show some logging and see what it's doing. This script basically connects to the Kafka bus and is gonna wait for that interface to come up. That's the logic that I wrote. It's gonna wait for messages to the Kafka bus that are coming every 10 seconds, and it's gonna wait a maximum of 30 seconds for any evidence that the interface came up, okay? So right now it's consuming messages. Those messages, if we look here, those messages continue to trickle in. And at some point, we're gonna get either true or false. Okay, so we saw here a false. So basically we timed out, waiting for 30 seconds. Obviously the interface is down because it hasn't been configured yet. So the script that deploys, reads the JSON file, configures the interface, validates the interface, configures BGP and validates BGP is called deploy peer. And I'm not gonna bore you with all the details, but I just wanted to mention it just in case you examine this later. Basically, this is kind of an Uber script that just reuses these other 4 scripts, okay? So what I did right now was just to run this script in isolation, okay? Just to show you the logic of the validation, okay? So let's run this guy. And I'm gonna do 2 things. I'm gonna time the execution for extra dramatic effect. And we're gonna ask for logging. Let me show you something first. Remember, all the configuration is in this JSON file. So we're gonna deploy from there, and I'm gonna use -v because I wanna see all the logging of what is happening, okay? So the first thing that the script did, it's executing fast. The first thing that the script did was to read the JSON file, right? This JSON file. It connected to the Kafka bus, and it sent the interface configuration. Okay, this is the XML representation of the interface configuration. It waited for confirmation. This OK came back because it means the script the validation script was able, within 30 seconds, was able to get at least one message from the Kafka box indicating that this interface came up, okay? At that point, it moved to the configuration of BGP. And this is my BGP object that we saw before. This is the global configuration. This is my neighbor configuration, and this is the peer group, okay? So it was sent to the router, and it waited for the Kafka bus to indicate that that neighbor is up. And it printed OK when it was able to get the message. And the execution roughly concluded in 32 seconds. Okay? So in 32 seconds, it did the interface configuration, waited for the interface to come up, got the message without pulling the router, got the message from Kafka. When he got the message from Kafka from the message bus, pushed the BGP configuration and waited for the state to come up and got the OK. I'm going to run it one more time. So anybody wild guess what is going to be different this time? The execution time is should be, hopefully, if everything goes fine, should be much faster. Why? Because the validation is going to be way faster. Before, we need to wait for the interface to come up and for the next streaming message or Kafka message to indicate that the interface came up. Also, we have to wait for the BGP state to come up, right? And for that to be sent via telemetry and for the Kafka message to come to me before I could report that the deployment was successful. Now, because the state, the sessions are already there, basically I'm reconfiguring something that is already configured, and I just need to wait for the next telemetry message, the next Kafka message. So hopefully it should be much faster. And I'm gonna run it without the debugs because I think you've seen enough debugs already. Okay. So we see that instead of taking the 31 seconds in this case, just took it much faster, 11 seconds. Okay. Any questions on that? Okay. So basically, what we just saw this workflow going from the JSON file to configuring the interface, to configuring BGP and be able to validate all that. So the details of what were the ingredients that went into this. I'm putting here the details of the models. As I mentioned at the very beginning of the presentation, the intent here wasn't necessarily to show you the latest and greatest models, but show you what is possible today with actually, this is a real implementation on a real release product. Everything that is here it's implemented on or can be implemented on production software. Okay, so those are the details of the versions of the 4 models that we use: the routing policy, telemetry, interfaces, and BGP. The version of the APIs of the SDK that we use, the versions of Pipeline, Kafka, and Zookeeper. All this stuff is pre-configured, pre-packaged on the Vagrant box. I'm going to put the Vagrant box on that repo at the top. I have to push it right after this. So I would say probably by the end of the day, you should see a commit on that repo with all the details of the Vagrant box. So summary. Hopefully this presentation gave you a quick overview of kind of the next level of detail. If you ever attended just a high-level introduction of OpenConfig, kind of give you a close-up to a first set of models. Kind of understand at a very high level the design patterns that you're going to see in the models. We saw some of the structure of 4 key models: BGP, routing policies, interfaces, and telemetry. And we saw that those models actually you can start implementing some real life, some real world use cases with the models. Okay. Any questions? Jeff. Leave us on a high note.
So question to either you or Anis. So very right concern, how do I make sure my intended configuration is not going to break? It's going to be working as intended, right? So going back to ATF, we released MDA.
The idea of the validation, how are you going
so,
on the asking on the intended versus applied config?
Yeah, so on the ATF side of things, you could use different data stores and user PC structures and filters to fetch this data and compare one to another. How would we do it here?
My validation for this demo obviously was as trivial as it could be, right? I'm just looking for this particular field, and that
You
field is
validate
okay.
semantics against data model. You don't validate intent.
But for instance, something that I didn't do was to validate, for instance, that the applied config was actually the intended config, right? Yes. So as I said before, this is not meant to be the basis for your automation framework in your company. So don't go back saying, hey, I'm doing it this way.
Because you are taking step 3. You are configuring stuff and assuming it's working. It might be not.
Yeah, so definitely validate. There's more to validate in real life. Yes.
Hey, a couple questions, maybe more for Anis, who's right behind me here. I was curious, one, if there was any thought given to moving the state to its own tree instead of having it mix in with sort of the config, so that, you know, right now if you look at the config tree, you see, you know, the config node and the state is right next to it. So for storing things in database and stuff, that's, I don't know, it makes some of the implementations a little interesting. And then the other piece is regarding the telemetry stuff, there doesn't seem to be any documentation at all about the telemetry out there, at least that I could find. It's great to see it here and you know, how it's configured and what it's supposed to do and all that stuff. Just wondering if there was anything outside of the actual Yang models itself from the OpenConfig team.
So on the first question regarding the structure of the model, I'll let probably Anis talk about the trade-offs and the why, the logic behind the quote-unquote madness. I'm sure there's a reason for everything, a good reason. On the second one, telemetry, I mean, models are self-documented. For instance, the APIs generate all the documentation based on the model. But in addition to that, I can speak for Cisco, but I'm sure for other vendors, there's functionality documentation. We have documentation and we have a lot of blogs and actually tutorials on telemetry. So XRDocs is one that we use. If you haven't used, you can probably Google that. XRDocs probably has at least 7 or 8 tutorials on telemetry.
So I'll try to answer Jeff's question. So the notion of being able to validate intended versus applied configuration is really, the intention of that model structure is to allow you to basically push your intended configuration. You can read back configuration data, either using a get or via streaming telemetry. So you can actually send back in the telemetry stream both config and state data, right? And then the idea is that you get back config data, the intended config, you can also get back the applied data and you can compare. On systems where you have sort of full transactionality, those things should generally be the same. But we wanted to allow for systems where you have some form of eventual consistency, which lots of distributed systems do that we use in software systems that run networks now. So the idea is that you can actually see the difference and see the convergence also. So you can not only check that what you pushed as intended config was in fact received by the device as intended config, like a get config call, but you can also see the applied state in the state telemetry stream. Now, to answer Kevin's question on structure of the state versus config, there's several documents written about the rationale for why we structured the models with config and state containers together. The main reason was to allow a very simple way, almost just a purely programmatic way, to be able to relate the state and configuration data. So to do exactly what Jeff was asking about, which is to be able to say, is my intended config matched with my applied config? And then can I see the other related derived state that's associated with that configuration? So that's the reason that they're together. I agree that it does raise some other challenges as far as how you store. It may be a bit more work to actually coalesce all the state data if you want to put it all in a separate database from your config data. That is true, but the trade-off is that you have a very simple programmatic way to get to both config and related state data. And lastly, I think about the telemetry documentation. To be honest, we haven't spent a ton of time on the telemetry config model that Santiago went through. Most of our focus, at least speaking from our organization, has been on using streaming telemetry where it's an inline process. The collector subscribes to the device and it gets streams of data. And for that, you know, at least with gRPC, we've defined the GNMI protocol, and there's actually quite a bit of documentation about how telemetry subscriptions work in a streaming fashion using GNMI. That said, we need to give some more attention to the telemetry config model. We just haven't gotten around to it.
There's GNMI draft written by you that needs to be updated. Is this so? It's very readable.
Yeah,
and
it's expired. It's going to get updated. Sorry, Jeff.
Yeah, so there's a subscribe RPC defining GNMI that takes care of that lean model.
I have a quick question. Like,
Sure.
does the model like describe like how can we modify existing configuration? Say, I want to insert a specific policy to a existing BGP policy. I don't see that the current model.
If the model can specify how I can change the policy?
Yeah, like how can like modify an existing, like say container or like sequence of configuration?
So that's probably a conversation that can be even had over beer. Let me just say in general that Yang, I think, is a fairly expressive language. There's a lot of attributes, constraints, dependencies that you can define. The flip side of that is that, well, there are two things. All possible corner cases, probably you cannot specify in Yang. And if you try to specify every single corner case, you're going to end up with a Yang model that is humongous. So I don't know exactly the case that you're saying, but in most models, there's actually a fairly good amount of definition of what's valid and not valid. There should be very unlikely that you define something that is valid to the model and the device will consider it not valid.
It's quite common, like for you, like to insert like a specific, say, access control list to an existing ACL, or put like a policy, BGP policy in an existing policy. Like say, like when you do redistribution, you always have like a deny all in the very end, but you want to insert like a specific policy like before the deny all, so that means you cannot just like simply append it to a.
To me, it looks like an insertion in an ordered list, and that you can certainly do in Yang. Yes.
This is somewhat related. I'm dying, Carlos. Somewhat related to the previous question. In netconf, you have the option to specify that a section of the tree is supposed to be replaced or inserted or merged, right?
Yeah. Or created,
so,
or. Yeah.
I noticed that your tools were generating the XML that then was sent over netconf. And is there a flag somewhere in the Yang model where you can say this?
No, it doesn't have to do anything with the Yang model. The Yang model is just defining the structure of the data, right, and constraints of the data. In this case, I was using an SDK that was abstracting netconf for me, and it was abstracting it in terms of a create, read, update, and delete operations, right? And in the particular SDK that I'm using, I'm saying, hey, I want to create this object. And the way the SDK translates a create operation is into edit config in netconf with the merge operation. In the SDK, in YDK, if you want to have direct access to netconf and be able to specify very particular what kind of operation of netconf, where you want to do a replace, the SDK also allows you to do that.
Nice, thank you.
Yes. Any other question? All right, guys, thanks for coming.